Oh no, you hit the wall! Stop asking your mom for your stuff. Lucky you, you have Pac-Man to solve your problems.
MDP Group 2.
Shall we begin on our story?
Very cute, very cute.
The API is the coordinator of the whole system that facilitates exchange of data between other modules. In this project, we harness the power of the API to create a dedicated Wi-Fi network for communication with the algorithm and image recognition server. Bluetooth communication ports were also set up to allow exchange of information with the Android tablet. The user established a direct link between a Raspberry Pi and an STM board through a USB connection, enabling a swift and dependable data exchange. We utilize Python multithreading to allow for concurrent processes, thus enhancing the overall performance of the system. The API program is also built to handle connection breakdowns, enhancing its reliability. The software for each service was designed to facilitate the seamless exchange of data, resulting in a cohesive and high-functional system. With these implementations, our project stands as a testament to effective collaboration between hardware and software elements.
The robot, powered by an STM32 board, is the foundation of all other parts. We built a card that can receive and execute commands from Raspberry Pi to accomplish different tasks. In addition, many sensors like ultrasonic, infrared, and built-in gyroscope are applied to help the robot to achieve the goal. Precision and reliability are the most important features that we target to work on. The reason is that we only have 3 chances in total for 2 tasks, and we have to make sure that the robot can precisely execute every single instruction sent by Raspberry Pi. Therefore, most of our work is to integrate the robot to be faster and faster within our control.
The Android application enables communication between users and the robot, allowing us to control its movements and retrieve the images recognized from the image recognition task. Our UI design is inspired by Pac-Man, an action maze chase video game. We hope that by incorporating the Pac-Man theme into our app, it creates a fun and competitive game-like environment for users. The homepage allows the user to navigate to our 3 main pages: Arena, Bluetooth, and Messages. The Bluetooth page allows users to scan for nearby devices and connect to their desired device. We can turn Bluetooth on and off and see which device the tablet is connected to. In the paired devices list, we are easily able to select from devices we were previously connected to. Alternatively, we can connect to nearby devices from the nearby devices list and tap on the refresh button to scan for new devices. At the communication page, you may send customized messages to the RPi and view the message logs between you and the RPi. On the Arena page, you can see the 20x20 layout grid of our image recognition maze. We can update the coordinates of the obstacles on the grid by tapping the Set button. Then, we can drag the obstacles onto the grid to the respective coordinates. Then, click Done to fix the obstacles. Obstacles can only be moved when the Set button is pressed to prevent accidental moves. After setting the position of obstacles, the face of the image on the obstacle can be set by tapping on it. Click Save, and the coordinates and direction of the obstacles are sent to the connected RPi. The red arrow buttons at the bottom center of the screen can be used to control the robot's movement. To begin the image recognition task, you can tap on the IR button to start the robot's movement. The application will then animate the movement on the grid to simulate the real-time movement of the robot. Below the grid, there is also a status indicator, coordinates of the robot's position, the direction of the robot, a Bluetooth connection status indicator, which are all updated in real time. Upon receiving the image ID of the recognized image, the app will update the correct image on the tablet along with its ID. As the robot begins moving, there is also a timer for users to track the duration of the task. You can choose to stop this timer at any moment with the stop button. As for the shortest path task, simply tap on the ST button without setting any obstacles, and the robot will begin its journey.
We collected 7,000 images of different environments, lighting conditions, distances, and angles for our dataset.
Afterwards, we used RoboFlow for our data annotation, pre-processing, and augmentation.
Our images were labeled individually with their corresponding image ID. We generated augmented versions of each image in our training set by applying grayscale, differing brightness, and exposure levels, resulting in a dataset of 17,984 images, where it is randomly split into train set, valid set, and test set.
Our image recognition server allows us to run photos taken on our model. We first load our model with the weights we got from our training stage. Using the image ZMQ library, we are able to transport the images from our RPi and save it in the data folder, predict it with our loaded model, and save the image with the predicted bounding boxes in our runs folder. The image ID predicted will be returned. In the case where the model predicts more than one image ID, it will return the ID that corresponds to the biggest bounding box.
For the algorithm, we first obtained the Hamiltonian path for all obstacles via a brute force approach where all possible paths were generated without picking the one that was the shortest. Then, pathfinding used the A-star algorithm with a heuristic of the Manhattan distance between current and end tiles, and the cost was modified by what type of turn the robot was taking. In real-world conditions, the robot may not precisely follow the exact path the algorithm produces. To account for these slight errors, we ensured that the robot would navigate to a sufficiently far distance from each obstacle so that it had a higher chance of capturing the image.